All right, so I cut my video off just in a weird spot. So I'm just picking up where I left off. So we were looking at this, okay? All right, where we had created the probability distribution table here. All right, so we had all of those, and then we wound up doing the expected value by taking the probability of getting a particular outcome. So let me show you this part. So we took the probability of getting a particular outcome times the number of heads. So the probability of getting no heads was 1/16, one head was 1/4, two heads was 3/8, and so on. All right, and so when we multiplied all that up and simplified, we wound up with 2. And then the question was, is this reasonable? We said yes, because you'd expect to get heads half the time. Okay. All right. So in this video, we're going to go from there and kind of formalize it a little bit and then look at a few examples. Okay. So what we just did, let me bring that down just a little bit. What we just did right here is what I want you to think about when you see this formula. This formula is how you calculate the expected value, okay, for when you're tossing a coin, or in this case, it was flipping a coin 4 times. The expected value of getting heads is what we were doing. So we were doing the expected value of getting heads. All right, and that's this. And then what x1, x2, x3, and x4, etc. represent were, no heads, 1 head, 2 heads, 3 heads, 4 heads. And then the probability of getting no heads was 1 out of 16. 1 head was 1 out of 4, 2 heads, and so on. So we did that calculation. 3 heads, the probability was 1/4. 4 heads, the probability was 1/16. That's how we would calculate the expected value of getting heads when flipping a coin. Okay. And so then we simplified all that and got 2. All right. So that's what that formula represents. So it looks complicated, but it's really not. That's how you calculate it. Now, the idea of, or this concept of expected value can be used to determine like if you're playing a game, like you're gambling, which, anyway, so if you're doing some kind of a game where you receive money, or where you have to pay to play the game, you can assess whether the game is fair or not by looking at these conditions. So anyway, so if the values of this random variable that we're doing have to do with how much money you win or lose in a game, then instead of just calling it expected value, it's the expected net winnings. Okay. And if the expected net winnings is 0, then the game is fair. That's what it means to be a fair game. So it's not biased in favor of the player or against the player. Okay. And then if the expected net winnings is negative, the game is unfair, and it's unfair against the player. If the expected net winnings is positive, it's unfair, but it's an unfair in favor of the player. Okay. All right. And then sometimes if a game is unfair, in favor of the player, then what we can do is adjust the ticket price or the cost of the raffle ticket so that the expected value winds up being fair, winds up being the net winnings wind up being 0, and the game would be considered fair. So let's do a problem or two and get the hang of this. So we're going to do a couple problems that deal with just rolling a die. All right. So the first problem says we got a game, we're going to roll a single fair die. So before we even get started on that, we know the outcomes of rolling a fair die would be the numbers 1, 2, 3, 4, 5, or 6. Move that up a little bit. Okay. And we know there's a equal chance of getting any one of those numbers. So a 1 out of 6 chance of getting any one of those. All right, so let's see what happens here. All right, so with this game, if an even number of spots turns up, you receive as many dollars as there are spots. If an odd number shows up, you have to pay as many dollars as there are spots. Okay, so we're supposed to find the expected net winnings. Okay. All right, so to do on A, to work that out, okay, if for this first case, if we get a 1 on the die, the probability of that happening is 1/6, and the payout would be -$1. Okay. The probability of getting 2 would be 1/6, and the payout would be a positive $2. Okay. Then if you got a 3, the probability would be 1/6, and the payout would be -$3. Okay, if you got a 4, you'd receive $4, and the probability of getting a 4 would be 1/6. Getting a 5, you'd owe 5. Probability would be 1/6. And for 6, you'd receive 6, and the probability would be 1/6. All right, now it really helps actually not to reduce the fractions, because all of these would have a denominator of 6, which would make it easier to add up without a calculator. So I'm just going to go through and I'm doing the multiplying first. And then I'm going to see what I wind up with. So here I have -1/6 and 5/6 would be -6/6. So that would cancel out. And then if I do 2/6 minus 3/6, that's -1/6 plus 4/6. So all of that adds up to be 3/6, which is 1/2. All right, so the expected net winnings of the game would be 50 cents. That would be your answer to A. Okay, now let me move down here, give myself a little room. Okay, now in part B, we're being asked to determine if the game is fair or if it's unfair against the player or unfair in favor. Okay, so since the net winnings turned out to be positive 0.50, it's unfair since it didn't turn out to be 0. To be fair, the expected net winnings needs to be 0. So it's unfair, and it's fair in favor of the player since it was positive. Okay. All right, let's try another one that involves the die, just a different payout. Okay, so we already know 1, 2, 3, 4, 5, 6, that the probability is 1/6 in each instance. We already know that. Okay, now it says we get $3 for a 6, 2 for a 5, and 1 for a 4, and no payoff otherwise. So for A, if we get a 1, we get no payout, and there's a 1/6 of a chance that would happen. If we get a 2, there's no payout, and there's a 1 out of 6 chance that would happen. No payout for a 3. So I'm thinking about this like a 1, a 2, getting a 3. Okay. Oops, that should be a plus right there. Okay. And then if we get a 4, we get $1 payout, positive. And a 5, we get a $2 payout. There's a 6th chance of getting a 5, and there's a 1 out of 6 chance of getting a 6. We get a $3 payout. Okay, so that would be 0 plus 0 plus 0 plus 1/6 plus 2/6 plus 3/6. All right, so see how that adds up to be 1, 2, 3, 4, 5, 6/6, which is 1. So the expected winnings for the game would be $1. So if we were going to set the price of the game, we want it to be a fair price, we should set the price at $1. That's B. Okay. All right, let's do question number 3. This one, it says a certain game involves tossing 3 fair coins. It pays 10 cents for heads, 3 heads, 5 cents for 2 heads, and 1 head, you'll get 3 cents. Okay. All right. So let me go ahead and do a tree diagram real quick. So we would get either heads or tails. Okay. And let's see, how many times 3 fair coins? Okay. Heads or tails on each of those. And then we could get heads or tails on each of those. So we just have 8 branches. So let's list all the outcomes. We could get all heads. Okay, let me just go ahead and follow the branches and write down all the possibilities here. Okay, let's see. THT, TTH, and then TTT. All right, so those are all the possibilities. There's 8 of them, right? And then you could get, the game deals with how many heads you get. So we want X to be the number of heads. And we have, and then we want the probability of that happening. Let me just use P. Okay, and you could get no heads, 1, 2, or 3, because we're only tossing the coin 3 times. All right, so no heads, it's only 1 possibility out of 8. 1 head, we've got 1. Oops, I circled the wrong one. Okay, we have 1, 2, 3, it appears, 3 eights. Okay, and then 2 heads, let me do it in a different color. Would be 1, here's 2 here, 2 there, there's 3 there as well. And for 3 heads, we have 1 possibility out of 8. Okay, so there's our distribution, probability distribution table. All right, let me give myself a little more room. I'll move that up. So let me fix that real quick. Heads or tails. Okay, so that's okay. And there was our 3. Okay. All right. So now let me go ahead and do the expected value. So do the expected value of getting heads. Okay. Would equal, and let's see now. So when we do this, we get 10 cents for 3 heads, 5 for 2, 3 for 1, and then nothing if you don't get any heads. So no heads, probability is 1/8. The payoff is $0. Okay. Okay. For 1 head, the probability is 3/8, and the payoff is 1. Oops, not dollars. Let me do cents. 0 cents, 1 cent, 0 cents. So 1 head, it is 1 head is 3 cents. Okay, let me get that straight. Okay, probability of 2 heads is 3/8, and the payout for 2 heads is 5 cents. And then the probability of getting 3 heads is 1/8. But if you do, you get 10 cents. Okay. All right, so that turns out to be 0 plus 9/8 plus 15/8 plus 10/8. I like to keep them all 8s, so that's 24. That's 34 eighths. Okay, and that, let's see, 8 goes into 34 4 times. That's 4 2/8. That's 4 1/4. That would be 4 1/4 cents. Okay, so that'd be your expected winnings, would be 4 1/4 cents. So now the question is 5 cents fair? And the answer would be no, because your expected winnings are 1/4 of 4 1/4 cents. But if you paid 5 cents, do you see how your expected net winnings would be negative 3/4? Okay, that would be unfair against the player. So if you wanted it to be fair, you would have to charge 4 1/4 cents, which you really couldn't do. But okay. All right, so I'm going to stop this, and then we're going to do a few more expected value problems that get out of that context of just games with payoffs. We're going to do some raffles. We're going to do this thing about absences, and then I'll see if I can squeeze in the last example dealing with making a business decision using expected value. Okay.